Today we are going to start variation method. Okay. Introduction we have already done. So in variation method, what we do, we first we have to choose one trial wave function, right? So if because in variation method, Hamiltonian is known to us, but wave function is unknown for the system. So that's why we select trial wave functions and we apply variation principle, means we evaluate the integral, okay, which provide us the value of energy. If the energy that we are getting by variation principle, if it is close to or nearest to your ground state energy or the true value, so that wave function, that corresponding wave function will be the best approximation to that system. Okay. So here we will choose one trial wave function that will be the linear combination of eigenfunctions. Okay. So here we can write, let the trial wave function, let the trial wave function for any system, for any system is linear combination of, is linear combination of eigenwave functions. Eigenwave functions. Okay. So how to write the trial wave function? So psi is the trial wave function. It is a linear combination. So here we will include some variable parameters also. C1, phi1 plus C2, phi2. Up to two terms we will take the wave function. Okay. Suppose in a molecule, suppose there is a molecule like helium, and in helium, how many nuclei present? Two nuclei present. Helium 2 does not exist. You can consider any other homoatomic molecule, A2. Okay, and in this two nuclei exist. Okay, two nucleus exist. So let's suppose the phi1 is the atomic orbital for your first atom, and psi2 represent the atomic or the eigenwave function for second nuclei. Okay. So this trial wave function, it's a linear combination of two eigen functions where phi1 and phi2, these are eigen functions. These are eigen functions. And C1 and C2, what are these? These are variable parameters. These are variable parameters that can be varied to get the minimum value of energy. Okay. So to this wave function, we will apply variation principle. Okay. So in the previous lecture, you have written few steps. First was the selection of the trial wave function that we have done. Second was the evaluation of the integral. Okay. So according to variation principle, the energy for this system, it is given by this integral. Psi star h cap psi d2, and then psi star psi d2, right? So this is the integral that we will use to find out the energy. Now we will substitute psi expression here. E equals to integration. What is psi? Psi is C1 phi1 plus C2 phi2 star h cap, again C1 phi1 plus C2 phi 2. Okay, D tau. Similarly, in the denominator also, put the wave function expression in this way. Whole start. Is this step clear, students? I just have substituted the expression. Okay. Now what will be our next step? In next step, we will solve these integrals. We will solve the brackets. Okay. So you know psi1 and psi2, these are eigenfunctions and these are real functions. Okay. Psi1 and psi2, these are real functions. So let's multiply or solve these integrals. E equals to, see, here we have this term C1 psi1 and we have this term C1 psi1 of the second bracket, and in between these we have one operator. This is an operator. Okay, so when you multiply the first term of the first bracket with this term of the second bracket, you have to take care of the position of the operator. Okay, so how to write? First we will multiply this term with this one. Okay, so it will be C1 phi 1 C1 phi 1. So C1, because it's a constant, a constant value. So C1 square integration, we have phi 1, but between these wave function we have some operator, so we have to write operator here. Is it clear? You cannot write in this way phi 1 h. No, you cannot change the position. If h is coming in between these two functions, then you cannot change the position. You have to put it in between these wave functions. So first we have wave function, then we have operator, and then we have another wave function. So in this way you will solve it. Second, we will multiply this term with a second. So here we have C1 and C2. Okay, integration start, psi1 wave function, and this Hamiltonian we have to write over here. Okay, then phi 2. Is it clear? Similarly, multiply this with this C2 C1, C2 C1, integration phi 2 star. Here also you can put star. Phi 2 star, then we have h cap in between, and phi 1 d 2 plus, again we have C2 whole square, integration phi 2 star, we have Hamiltonian operator in between, and phi 2 d 2, then divided by, student, is this step clear? Let me know. We just have simplified the brackets. Okay. Okay, now similarly solve the denominator part also. In denominator, we do not have any operator between these two brackets. So multiply this first term with the first, you will get C1 whole square, C1 whole square, in integration we have phi 1 square, right? Phi 1 square, we can write phi 1 square because there is no operator in between. So we can direct multiply d2. Then C1 C2 phi 1 phi 2 d2. Then C2 C1 phi 2 phi 1. Okay, because as I said, phi 2 or phi 1, phi 2, these are real. Okay, so the star on it, it will not change the wave function. It will not change. You can put star, it's your wish, but that is not going to change the wave function. Okay, C2 square, phi 2 square, D2. Okay, so I hope this step is clear to all of you. Now, after solving the brackets, we will introduce a nomenclature which is given to these integrals. There are so many integrals present in this expression. Okay, so we will give the nomenclature. There is a nomenclature for these integrals. So let me write these integrals here one by one. So first integral is phi 1 h cap phi 1. Okay, d2. This is the first integral. Second integral is phi 1 h cap phi 2. Third integral is phi 2 h cap phi 1. Okay, next integral is phi 2 h cap phi 2 d2. Then phi 1 square or phi 1 phi 1. Okay, phi 1 square d2. Then phi 1 phi 2 or phi 2 phi 1 d2 and phi 2 whole square. Okay, so students, the first integral is given the notation or nomenclature as h11, because here we have a Hamiltonian in between, so we represent it with h, and because the wave functions belongs to the first nuclei only, so it is h11. Okay, then second can be written as h again. So which two wave functions are used? 1 2, so here we will write 1 2. Okay, and here again we will write h, and what will be the notation? It will be written as h21. Similarly, this one written as h22. Now coming to this one, phi 1 square or phi 1 phi 1. Okay, these are known as overlap integrals. Okay, so which is written as, which is represented by s symbol. So it will be written as s11, because same kind of wave functions are used here, and this will be s12, this will be s21, and this will be s22. Okay, in this way we will give the nomenclature to all these integrals. Now we will use these integrals in the above expression. So now energy can be written as just wait a second. Okay, so here energy can be written as C1 square. First integral is named as H11 plus C1 C2. It is named as H12 plus C2 C1. It is named as H21, and the last one is H22. Okay, then divided by, it is divided by C1 square. First integral is in the denominator. It is given the nomenclature S11 plus C1 C2. It is S12, then C2 C1 S21, then C2 square S22. So these are the nomenclatures which are given to these integrals. Okay. But here we have two integrals that gives the same value. Okay. Which one? H12 and H21. Wait. So you see, out of these integrals, H12 is equal to H21. How? How these are equal? How H12 and H21 is equal? You know, H12 it is equal to phi 1 H phi 2, right? And H21 is equal to phi 2 H phi 1 d2. So you can see this Hamiltonian operator as it is Hermitian operator. So it is following Hermitian property. This is a Hermitian property. So that's why these two integrals are equal. Okay, these two integrals are equal because it follow Hermitian property. Is it clear? So H12 and H21 are equal. Also S12 and S21, these are also equal. These are also equal. Okay. So we will write H21 equals to H12 and we will write S21 equals to S12. Because in S1, S12 and S21, these are the simply multiplication of the wave function. Okay, and you will get the same. If you multiply two wave function, you will get the same result. If you change the order. Suppose you have two wave function like this. E raised to power iota phi 1. Okay, and phi 2 is e raised to power iota phi 2. If you multiply these two by changing the order, then you will get same result. Okay, that's why these integrals are equal. So we are using this property now in the above expression. If you have any question, you can ask. So energy can be written as E equals to C1 square H11 plus now C1 C2 H12 plus third term is also C2 C1 H12. So we can write twice of C1 C2 H12. Okay. Then C2 square H22 divided by C1 square S11 plus again this will be 2 C1 C2 S12 because both are equal. C2 square S22. Okay. So this is the final expression for energy. So in variation principle, we have completed two steps. First step was to choose the trial wave function that we have done. Second was the solution of to solve the integral that also we have done. Now you can see in the energy expression, we have two parameters C1 and C2, which will be minimized, which will be optimized to get the minimum value of energy. To how to minimize or how to optimize this energy value by using these variational parameters. So I told you the third step for minimization, what we do, we find the differentiation of E with respect to these parameters. So now third step is we will find curl E by curl C1, then we will put it equal to 0 and we will differentiate E with respect to C1 and C2, then we will put it equal to 0. Okay. So to do this step, we will cross multiply this denominator with E. So you will get E into C1 square S11 plus 2C1 C2 S12 plus C2 square S22 equals to C1 square H11 plus 2C1 C2 H12 plus C2 square H22. Okay. So we have just cross multiplied or rearranged the equation. So now we have linear equation. Now we will solve it. We will find differentiation of E with respect to C1. Okay. So we will find out. We will differentiate this whole equation. Suppose this is, here we have the product of two functions. First is energy term and second is this whole bracket. So we have two functions here. We will apply product rule and we will differentiate with respect to C1. So first function will remain as it is, E. We will differentiate this whole bracket term with respect to C1. So you will get 2C1 S11 plus, with respect to C1 we are differentiating. So you will get 2C2 S12, right? And the third term will be 0 because there is no C1. Then plus second term as it is, C1 square S11 plus 2C1 C2 S12 plus C2 whole square S22. Differentiation of first curl E by curl C1 equals to, now differentiation of this part. Please wait. Yeah, differentiation of this part. So I'm writing here 2C1 H11 plus 2C2 H12 and a third term, differentiation of third term will be 0. Okay. Is this clear, student? Differentiation step is clear? You can ask if you have any doubt. Yes, students?
Clear, ma'am.
Okay. Now we will solve it. Okay, as I said, after differentiation, what we do, we put curl E by curl C1 equals to 0. Okay, so in this whole step, here we have curl E by curl C1. So put it equal to 0. Then this whole term will get 0. Na? So by putting this differential factor equal to 0, you will get E 2C1 S11 plus 2C2 S12 equals to 2C1 H11 plus 2C2 H12, right? Now you can see in both the terms, on left hand side and on the right hand side, we have 2 which is common. So that will be cancelled out. Okay. So cancel out 2 on both sides and multiply E inside the bracket. You will get C1 S11 E plus C2 S12 E. Then 2C1 H11 plus 2C2 H12. Okay. Now we will rearrange the term. So here we will combine the term having C1 at one side and the terms containing C2 on the other side. Okay. So let's combine the similar terms. So here we have 2C1H11. Okay. So we will shift this term here. No need to write 2 because we have cancelled 2 already. No need to write 2 here. Okay. So we have C1 H11 minus C1 S11E. Okay. Then we will shift the second term also, which is C2 S12E. And this whole equal to 0. Now you can see in the first bracket C1 is common. So we can write it as C1 H11 minus S11E plus C2 H12 minus S12E equals to 0. So this is the first equation that we got after differentiating E with respect to C1. Similarly, we will differentiate the above equation with respect to C2. Okay. And what result we will get? So here I will write similarly. Similarly, we will differentiate curl E with respect to curl C2. Okay. And what kind of result you will get? There is no need to solve it. Okay. We will directly write the result. So the equation that you will get after solving this, you will get C1 here. This kind of equation you will get. There will be bit difference. So this term, which is written on the second side, this will come over here. But the number will exchange like this. Here we have H12, but here we will get H21. Similarly, S21E. Okay. And here, this term we will write over here, but with here we are getting H11, but here you will get H22 because here we are differentiating with respect to C2. So this will be the only difference in the equation. I hope this is clear. Even you can differentiate with respect to C2 and you can do all these steps, you will get this one only. Okay, so you will get these two equations. These two equations are known as secular equations, which is giving non-trivial solution. Secular equations, and we can generate a determinant using these secular equations. Okay, a determinant is generated using these secular equations. So you can see here we have two terms row wise and two terms column wise. Means, see, this is the first term, this is the second term. So in a row we have two terms, in a column also we have two terms, right? So we will generate a determinant of the order 2 by 2. Wait a second. Yes. So we can generate a determinant using these two equations, and the determinant will be written as, the first term is H11. Do not write C1. S11E. Okay, this is the first term of the determinant, and second term is H12 minus S12E. Then H21 minus S21E, and here you will write H22 minus S22E. So this is the determinant of 2 by 2 order, and the result is equal to 0. Okay, by using this integral, we can find out the energies. If you know the integral values, you can find out the energies. Okay. So students, there is one, we can further modify this integral. Okay, if we use orthonormal basis, what does it mean? If we apply orthonormal basis to these integrals, means, you know, in these integral, which wave functions are present? Phi 1, phi 2, right? So in S11, which is equals to integration of phi 1 square. If we apply orthonormal condition to this, then this will be equal to 1, because you know the normalization condition. Okay. And similarly S22, which is integration of psi 2 whole square, this is also equal to 1. And these integrals S12 it is phi 1, phi 2, d2. Okay, and if this is equal to 0, if we apply orthonormal basis set S2, sorry, phi 2, phi 1, d2, this is also equal to 0. Then this determinant can be reduced to, it can be written as determinant H11 minus E, right? And here you will write H12 because S12 is 0. Here you will write H21 only. And here you will write H22 minus E and put it equal to 0. So student, on this is very important in determinant, because on this determinant you can have numericals. Okay. So here we have completed this topic. We have, this is the derivation of variation principle which we have applied to any trial wave function. Okay. So if you know the values of these integral, then you can calculate energy, right? So I'll give you one question similar to this based upon this determinant. Just wait a second. Till that time, you can ask me any question or query if you have. Students, can you see the question?
Yes, ma'am.
Okay. So this type of question you can expect from this topic.